Hey guys, welcome to another episode of Robo Papers. I'm super glad today to have Colin Lee and Paul Zhou. They are the authors of this paper called Reinforcement Learning with Action Chunking. And so really happy to have you guys to talk about the paper. Maybe as a start, I think Colin, you can introduce yourself, and Paul, this is the second time, but you should introduce yourself as well. But Colin, you can go first.
Yeah, no, thanks Michael and Chris for inviting us. So my name is Colin. I'm a UC Berkeley student working with Professor Sergey Levin. And my interest is in reinforcement learning and how do you do online exploration efficiently from all of my prior experiences, and a little bit also on the robot learning side.
Yep.
Cool.
I'm Paul. Yeah, thanks for having me back again. Really glad to come back and
Great to
chat
have
about
you.
our paper.
Mhm.
Yeah, so I'm Paul. I'm a third-year PhD student at Berkeley working with Sergey, and my interest is in reinforcement learning and robot learning, and how to, most importantly, how to use RL to fine-tune robot foundation models, to robustify skills, to acquire new skills.
As the title of the paper suggests, what our paper is trying to do is how do we actually do reinforcement learning with action chunking policy. In imitation learning, a lot of people have used action chunking and it has a lot of very good benefit, right? And I always thought, okay, it would be a really good idea if we can somehow get it to work in TD-based RL or Q learning in reinforcement learning. And it turns out that rather than just a simple adaptation, action chunking policies in TD learning or reinforcement learning with Q learning actually has some very good benefits. I guess as what we talk about in a bit, we'll show that this actually leads to better online exploration. And this is mainly due to the fact that action chunking policy would exhibit temporally coherent actions. And something a little bit more specific to the Q learning framework that we're working with, action chunking policy or learning Q function that's taking the entire action chunk actually leads to better or faster value backup.
For the sake of anyone listening, maybe could you explain what action chunking is?
Yeah, of course.
Yeah,
So
for the sake of me as well. and also like what is exactly action chunking, and to your point, how is it being used in imitation learning? Right, first, and then if you can.
Yeah. Okay. Of course. So stepping back a little bit, so what a normal policy or a one-step policy, what it does is it takes in a state at a time, and then output an action at each individual time step. Right. So if we use this, can you guys see my cursor actually, or is that visible? Okay.
Yeah, we can see
So
it.
if we reuse the same diagram here, at each time step t plus 1, t plus 2, we'll just produce one action given the current state and then do it over and over again. What action chunking policy does is that instead of producing one action at a time, it produces a short horizon of action sequence. So as we can follow the diagram here, from the state at time step t, it's going to produce an action chunk, what we call an action chunk, or just a sequence of actions for the current time step t plus 1, t plus 2, to a short horizon. Here, the horizon length is 5. But in general, it can be either longer or shorter. And in imitation learning, this is a good idea to actually produce action chunks and execute them in the open loop fashion, which means that we're just executing these predicted action chunks without even considering what happened in the state at the t plus 1, t plus 2, t plus 3, t plus 4. This has the benefit of sort of reducing the cognitive load of like actually predicting everything at each time step. And it also has the benefit that, it's like kind of like temporally coherent, because you imagine you can predict everything at once and you don't run the risk of like going back and forth of trying to go left and go right, because the entire action chunk is like kind of like going in the same direction. So
just to add to what Colin was just saying, like this idea has really been popularized by roboticists doing imitation learning. And like these days you'll find like all the top performing robot models that they all produce action chunk policies. So whether you're looking at a diffusion policy or at a VLA model, they all produce things like 50 actions given a single state. So this really helps you capture some of the non-Markovianness that you usually get in your offline data set that's teleopt in the robotic sense, or like simulated, generated, scripted in the RL sense. So So these ideas help capture like the non-Markovianness is like essential to getting good performance policies in robotics. And what Colin was saying a little bit before is that the idea here is whether we can try to use the same idea, whether we should and whether we can use action chunking in value-based RL to improve the performance.
Yeah, sorry, got it. Just to sum it up, right? So action chunking, you mentioned 50 actions, Paul. So 50 actions concretely roughly is what? Like how many seconds are you talking about? Like,
If you're doing 50 hertz, that's 1 second.
Roughly 1 second. So it's as if, okay, based on what I see now, the robot see, do 1 second of things, you ignore what happened in the next 1 second, you just do the thing. You could have bricked something in the middle, but you just do it anyway. And then 1 second later, you see the state again, you do the observation, and then you do that's effectively how a layman can think about it. Okay, cool. And basically this paper is talking about how do you think about it when it comes to RL.
Right. Yeah, so in the field of roboticists do a lot of different things with action chunking policies. Like you can open it, you can execute it like the full action chunk and then produce another action chunk, or you can execute half an action chunk and do other things. And then you can like merge these action chunks for robotics reasons. But here we're really just considering if you can produce a chunk policy and you just execute them one by one.
Okay, so I guess just a little bit of teaser of how well this does. On the right, we have an aggregated plot that shows that having this action chunking policies in RL is actually really effective, especially for online learning. So just to interpret the plot on the right a little bit, the first half of the plot on the left shows how well our method does with action chunking in the offline RL case. So offline RL is a setting where you learn directly from an offline data without any online interaction. And the action chunking RL really shines in the online case, which is the second half of the plot from where it shown on the right-hand side, where action chunking policy really outperforms previous non-chunked baselines by a lot. So I guess you guys want to know how it works?
How does it work?
Yeah.
Why is this hard to do why makes it hard to do action chunking for RL, I guess?
Yeah.
That's a nice way to lead in. Yeah.
Yeah,
that's
and maybe
really great point. Yeah.
Yeah, and maybe if I can just add one point before that is like, why do we want to do action chunking for RL? So I guess a lot of people reading this like might be wondering this, because if you want to try to learn a optimal policy in an MDP, which is a Markov decision process, like how all problems are formulated, you shouldn't have to output in action chunk to get your optimal policy. Your optimal policy can just output one single action based on your single time step. But our observation here is actually the real effectiveness of action chunking, as Colin said, is in the online RL phase or in the offline to online RL phase, where it really induces efficient exploration. So the intuition for that, your mental model could be because the RL, if you're training it in action chunk space, you're capturing these temporal coherencies in your offline data set. So instead of saying when you see a muck, you need to put the gripper down like 1 centimeters, you're saying when you see the muck, you want to put your gripper like towards the muck and grab it by the handle. So if you have these kind of temporal coherent notions of what essentially a skill is, then you get much more efficient or directed exploration online, and that makes your offline to online RL much more efficient.
Makes sense.
And then Colin can tell you about how all of this magic actually works behind the scenes.
So I guess before we start on talking about like how exactly it works, maybe first we should talk about a little bit of the first thing we tried. So let's switch to the paper, and this will actually kind of give some idea of like why doing action chunking with RL is not simple. So the first thing we actually tried was to, let's say, given an online RL algorithm out of the box, can we just simply do RL on this temporally extended action space? What does that mean? It means that we basically treat a small action horizon or like a horizon of action as the new action. So instead of saying that we do our action one at a time, we just literally treat, let's say, 5 actions together as our new action space. And then we're training this policy and a critic on both of them. So I guess more mathematically, it just means, okay, policy takes in action horizon, AT to T plus this is our action, and our critic is the same thing. We take the current action, the current state, and the action in the next each steps. And we can do RL exactly in the same fashion because we can literally say that, okay, look, we just ran the RL, but just on this temporary extended space. So we actually did that. And it turned out that this thing, if we just run this thing naively, it actually doesn't work very well. So the more concretely, the thing that we tried is that we take out of the box online RL method that can deal with prior data set, which is called RLPD. And it's one of very strong online RL method that can do very, very well. But if we actually just add action chunks or run this algorithm on the action chunking policy or the temporary extended action space, actually doesn't work very well. So let's take a look at this plot here. So RLPD, which is the triangle line, it doesn't use action chunking, and it kind of does okay on a lot of environments. But as soon as we add action chunking to this RL algorithm, it actually kind of breaks down. So this is the kind of the diamond line here. You can see that it actually doesn't work very well on these environments.
And that it actually works worse.
And it actually works
when you
worse,
look at it.
Which is something that's kind of interesting, right? So we found out that this is actually because in order for action chunking to work in RL, it really needs two key ingredients that we sort of identify in our paper. So the first key ingredient is that we have to use expressive enough policy to actually be able to capture the offline data set. So something to know, a little bit background here is that most of the online RL or the naive online RL methods, they actually use Gaussian policies. So what Gaussian policies is that it only captures a unimodal distribution in your offline data. And this really doesn't synergize well with action chunking policies to deal with non-normal covariance or the complex distribution in the offline data set. And that is why if we just naively combine whatever thing with online RL, it doesn't work very well. And then the second part of thing that's a little bit more nuanced is that we actually need to, so let's see, where is this? Yeah. So we actually need to impose a behavior constraint for our action trunking policy for it to work. What does it mean by behavior constraint? Do you guys have some intuitive understanding of what this behavior constraint means in general?
No, not really. Could you elaborate?
So yeah, let me elaborate a little bit more. So behavior constraint essentially means that for offline data set, we want to make sure our action chunking policies stays close to whatever behavior that is in the offline data. So as sort of the intuition that Paul explained a little bit earlier, if you want to sort of grab a cup where the task is about grasping things and moving pick and place, you really don't want to do any exploration or generate any behavior that is just jittering in space without actually moving to anywhere useful. What you actually want to do is to kind of adhere to the behavior that you already collected in a data set, which usually involves very coherent actions that's going towards certain object, picking up the object and putting the object down. So the idea of this behavior constraint is really to make sure our action chunking policy stays close to those behavior and not really generating actions that are not useful for solving the task or online exploration.
So let me give my intuition for how I understood this, just to make sure that we're on the same. So we have let's say a 6-DOF robot action space, and we have an action chunk length of 50. So you're sampling. So if you're just sampling on a Gaussian distribution or in a 300 dimensions, you're essentially just going to get something nonsensical, just move different. So just shaking your hand around in place and just do nothing. But you add in these behavioral constraints so that if it has to look like a trajectory from the action space, all of your samples will be meaningful, and that's why you're saying temporally coherent exploration. Is that right?
Yeah.
It'll probably get to something, right?
Yeah, that's correct.
Okay.
Yeah, that's basically it. Yeah. So essentially, you want to generate behavior that's just look like the trajectory in the offline data, but you still want the ability to be able to change away from that. So that's why we are only imposing a constraint, but not totally just imitating the behavior in the offline data.
You're learning your policy and your queue function over an action space of like 300 dimensions. And if you have no constraints, basically your queue function has a much more complicated landscape than if you learn on a single action space. And if you have no constraints, your policy can, if you're trying to maximize your queue function, your policy can get into like weird little maximums, as opposed to in a single non-chunked action space where the queue function landscape could look much smoother and you can get away without these kind of expressive behavior regularization.
Yeah, so I want to ask, like, as a follow-up, how much of that is needed? Like, is it specific to tasks? Is it sometimes there's a trade-off? Maybe you're giving it too much constraint. Is that the right way to think about it?
So in general, I think the amount of behavior constraint that you want to add to your algorithm really depends on the task that you're trying to solve. For tasks where you have data, for some tasks where the data has a very good or expert demonstration, you probably don't want to have a very weak constraint. You want to have stronger constraint because you know that it's already pretty optimal. You can just imitate and change a little bit, actually do well. So in our paper, we actually tune the amount or the strength of the behavior constraint for each of the domain, depending on how much the policy needs to change from the behavior prior.
But how do you make that call? Like, how do you make that judgment? Is that you feel the AGI and you decide, okay, this is how much you can give constraint, or is it also a learning parameter?
This is kind of just like one hyperparameter that you kind of have to tune. But you can tune it with the intuition, like Colin said, that like if you have some like for example more optimal offline data sets, such as like manipulation data sets that are all teleop demos, then you would expect you will want stronger regularization to this near optimal data set. But if you have something that's more like play data set, like exploratory data set, and you will probably want to tune a less regularization for that.
So, just to recap a little bit, what I just talked about is like we need two key ingredients of our algorithm to work. The first ingredient is like we really need a behavior constraint that makes sure the action chunking policy follows the offline data. And the second key ingredient is that we really need to have an expressive policy. Which means that we cannot just have Gaussian policy as the base policy parameterization. We have to use a more capable policy class, like a flow or diffusion policy, to really be able to capture the complex action chunking distribution as in the offline data. So this is where kind of like the practical implementation detail comes in, because it's sort of with a sort of expressive policy with our reinforcement learning. And this is a kind of like not a straightforward problem to tackle in general. So I guess in this section of the paper, we sort of describe two methods that we propose to really deal with how we can run reinforcement learning with this action chunking action space with the expressive policy class. So perhaps it's the easiest to directly jump to the algorithm box, because that's probably the easiest way to explain the algorithm. So the first algorithm that we propose is extremely simple. Actually, we just train a behavior policy, which we call F. So what this policy does is that it clones whatever that is in the offline data. So
through
it is
imitation
really
learning.
Sorry.
Through imitation learning.
Through imitation learning, precisely, yes. So it essentially clones the distribution of action chunks in the offline data. And the second part of the second network that we're going to learn is a critic, which is a queue function that provides the value of executing this action chunk at the current state. So essentially, it's like judging how good it will be if I were to execute this action chunk at a particular state. So how are we going to learn it, right? So what we're going to do is that we're going to use the normal TD backup loss for queue learning. But instead of using an actor to actually provide the action for the queue learning target, we're going to basically sample a bunch of action chunks from our behavior policy and pick the one that maximize our value network. So what does this mean? It basically means that we're doing some sort of like best of n in like, are you guys familiar with like sort of best of n sampling. Yeah. So we're sort of basically just saying that we want to do a best of n of our behavior policy, and we just treat that as our improved actor. And we're going to estimate what will be the value of this best of n improvement of the actor or the policy. And we found out that this very simple way of doing Q learning is actually really, really effective in practice. And this sort really helps us to simultaneously stay close to the behavior policy because all the action chunks are directly sampled from the behavior policy while being able to make use of a very expressive policy class.
Okay, interesting. So that's sort of like IMLE too, right? Somewhat similar.
So IMLE?
It's another imitation learning from demonstration method that came out a few months ago. But no,
really?
it's an interesting idea. I don't know. Maybe it's an interesting idea. It makes a lot of sense. But like this does mean that all of your action chunks are fairly restricted, right, to like what the policy, what you saw in the offline data. Do you think that would limit its ability to improve on like expert demonstrations or anything, or not really? Not a big.
So yeah, that's actually a fair point. And in our benchmark task, we didn't really find it to be a big issue, probably because there's still probably some noise in the expressive policy that it's generating. And we do have a fine-tuning procedure where our behavior policy continues to train the online data in the sense that whenever you have online rollout, the behavior policy is still trained on those as well. So it's like technically improving over time. But in the paper, we never ablated if that actually matters. So it's possible that is not needed. But in the algorithm makes sense, our algorithm can gradually improve by principle.
Yeah, and just to add on to that, at least personally, I think the role, at least like in like the field of robotics, the role of RL in fine-tuning policies is not that you don't want to learn things from scratch with reinforcement learning, right? You're really trying to take a base policy that's somewhat competent, that's trained with imitation learning, and then you're using RL to improve it. So you could see this as a kind of method that does that takes a pre-trained behavior cloning policy, trained exactly like how all robot models are trained today, just imitation learning with action chunks. And then you can do Q chunking on top of it to learn to improve it with reinforcement learning.
Q chunking means doing chunk critic, chunk policy, and use expressive policy. Okay, so I guess we just talk about this first algorithm here. And the good thing about kind of this recipe that we just talked about, using expressive policy, using chunked policy and critic, to do TD learning with behavior constraint is that this recipe is incredibly general. So we can actually apply this general technique or general recipe to existing offline to online RL algorithms, which are typically equipped with behavior constraint anyways. So the second algorithm is exactly doing that. It applies on top of an existing offline to online RL method called FQL. It's actually done by one of our colleagues, Zhou and me, where we developed like sort of like a distillation-based method where you can work with the expressive policy by doing the standard DPG style update without suffering from all the instability issue that comes with optimizing an expressive or diffusion full policy, right? I can go into a little bit more detail if you guys would like to learn more, but I figure maybe we could first kind of like go through the main point of this paper, which is like how well the action chunking can actually improve, like helps improve online exploration and value learning.
Yeah, that would be great. I think that makes a lot of sense.
But yeah, the point here is just that this Q chunking recipe is very general, that it can apply to existing offline to online RL methods, and we did try to do one instance, and it seemed to work pretty well.
And so you're using a flow matching loss, but you also did mention like diffusion, like a diffusion transformer would work as well.
Oh, yeah. So I would expect for the QC algorithm, it's really agnostic to the behavior, how the behavior policy is parameterized, because literally here we're just using it as a sampler.
Right. So it does need to be something you can draw samples from, like meaningfully, like rich samples quality.
Yeah, precisely. Yeah, then it will work. But for the FEO one, it's a little bit more specific to flow matching policy because we do need to use some distillation loss so that how FQL works is that it distills from a multi-step flow policy into a one-step policy. so that we can optimize it against the value function very easily. So that framework does sort of rely a little bit on the flow matching policy, but I think you can also get away with it by using the DDM sampler for the diffusion policy as well. But we didn't really try it in our paper.
Yeah, makes sense.
Yeah. Essentially, they're like just applying the same like behavior constraint idea to different kinds of behavior constraints.
Yeah. So along that line, we have a little bit of more mathematical justification on what the behavior constraint sort of means here. We can go into more details if you guys would like, but I guess like
I mean, I'd be curious to know how the behavior constraint is implemented, to talk more about that. But maybe we could go to the experiment, the results, and talk about this part first. Yeah, let's do that.
Okay, cool. All right. So yeah, let's just talk about results maybe. Okay, here. So we tested out a bunch of manipulation tasks from OG Bench, which is a recently proposed goal condition RL benchmark by Zhou, which is one of our colleagues in the lab. And it's a really good benchmark that contains a lot of very diverse tasks. They're also very long. Some of them are very long horizon and require sort of composition of multiple things. So, I guess what would be the best way to explain? I guess, okay. So roughly the ordering of these domains are from the easiest to the hardest. So puzzle 3x3 is the easiest, and then followed by scene, cube double, cube triple, and cube quadruple. So,
and just to give you guys a little bit of background on here, in case you don't know what these like task name means, basically these are a bunch of manipulation tasks where like one single robot arm is trying to do something interesting. Where the puzzle scene is there's a 3x3 grid of puzzles where you can so this will be easier.
Yes,
with
thank you for the visual aid.
Visualization. Yeah. So if you look at one of these picture after it loads on the second column to the right, the puzzle scene, the top one is the 3x3 puzzle where you can hit each button and then each button will flip the colors of all the adjacent buttons to it. And then basically your task is to press any button such that this whole board becomes the same color. So that's the puzzle scene. To the left of it is the scene, which consists of, it's a sequential task where you need to press buttons to unlock the drawer, open the drawer, to manipulate the little blocks, and there's a window to the right you can manipulate. And then the cube scene to the left of it is basically you have different numbers of cubes, and you need to pick and place it to different target locations, shown as the fainter colors.
Got it. So I think, so from looking at the tasks, so we have, it seems clear to me how it would be very useful to be drawing samples from a diffusion policy when you're doing exploration. So that's like, because there's like these very, I guess, clear things that it should be reaching towards and interacting with, which I guess is true for most tasks, right?
Yeah.
Cool.
And one thing I want to note here is like for some of the tasks, it really requires you to kind of like do multiple actions in a row in order to solve the task. For example, the scene task where you have to first like unlock the drawer and pull the drawer and then like put the cube in, like close the drawer, some sort of like that. So it sort of like requires you kind of to have some like long horizon reasoning, or like you can need to compose like multiple sort of primitives together.
Yeah. And so you can imagine these kinds of tasks or like these complex tasks in general are just very hard to do if you have a naive exploration phase online. What you really want across the board for these complex manipulation tasks is that you want to have structured exploration. You want to explore on the manifold of expert behavior, and that's what Q chunking really gives you.
Yeah, makes sense. Yeah, I think these are the kinds of things that we would have, I guess, people have tried to do for a long time with hierarchical RL. Is there any? But of course, I feel like the results there have never been all that, I guess, strong. Do you have any thoughts on how this compares to that?
Yeah, so we did try to compare to a skill-based method, which is like one of actually my prior work, sort of like training using like V to train like skill, and then you train like a high-level policy that gives the latent vector to this like low-level skill policy and to like explore in the maze. In general, what I found was that it usually doesn't do very well in the tasks that we sort of test in. especially for in the online case where it's not really able to improve that well in online. One thing that is sort of like that could explain why is that the sort of the skill-based method that I was experimenting with does not use online fine-tuning of the skills. So basically the skills are frozen, it cannot be changed. So whatever, if the skills were not perfect from the offline pre-training, then you can't really improve it online over time. And our method can do that because basically the all action chunks can be fine-tuned continuously online without a problem. That's sort of like maybe the conclusion that we got. So we will add the comparison, right? It's not in the paper right now, but we do plan to add the comparison in the next revision of our paper because we think it will be a really valuable comparison to the skill-based or hierarchical RL methods, just because they're sort of like a little bit pretty similar in some like sort of the formulation sense, but definitely our approach presents a very simple or simpler alternative to training a bi-level policy that removes a lot of like sort of instability training problem, where if you train like both level of policy, like high level, low level policy at the same time, it can cause some stability problem, which is why in a lot of work we freeze the low level policy and only train the high level policy, or we use some trick to actually make it more stable.
Yeah, it makes sense. Yeah, I think it's a really interesting comparison because they both seem to be aimed at the same goal of allowing you to do these longer horizon multi-step tasks. But this is definitely seems like a more elegant solution. Is that would you agree with that? Or
yeah, I do think it's a more elegant solution. I think there's more to be done, obviously, because there are some downsides to our action trunking policy. Obviously, it's like it probably is not as reactive as the skills. In case you do have these kind of like highly reactive, demanding tasks, like let's imagine you're controlling a car against a wind that's like blowing you at random speed, then
right.
Can't really expect an action trunking policy to do well, right, in general. But there are definitely trade-offs, but I do think for a lot of tasks that we care about in robotics, especially for manipulation, this is a much more elegant or convenient formulation to take or to use like a practical that allows you to really train non-Markovian policies or policy that can exhibit temporally coherent behavior relatively more practical.
So since you mentioned these more dynamic or reactive tasks, though, there's humanoids and ants in the column to the left there. Did you do any of these with your? We
tried. It never really improved. Sometimes it hurts because you can't. Yeah, that's sort of like
for that reason. That makes sense. So yeah,
but for that reason as well. Yeah. We tried it too.
Yeah. Oh, sorry. Yeah. So one thing I think that's really valuable in this space and in general is that to study how these action chunk policies could be executed, right? So like in this paper, basically the policy outputs a chunk and then we just execute a chunk one by one until the chunk has finished. But there's actually no requirement that you need to execute the full chunk. You could execute like one action and then recompute the entire chunk, or you can execute half a chunk and recompute the entire half a chunk. So one improvement like people could look into is that how you could dynamically select how much of your action chunk to execute given a particular task.
So one fun thing is that this project actually, the goal of this project actually started off as how do we actually do this? But we kind of like tried a bunch of things and it didn't really work better. So we just be like, okay, what if we just write a paper about action chunking policies directly?
Yeah, and it turns out that the simple things actually can give a lot of improvements in these domains. Yeah, but there is definitely a lot of research that needs to be done in this area.
Yeah, I definitely think having like a dynamical horizon or action chunk lens would be pretty valuable. And how to figure out how to do the value learning, which is like part that we were kind of like stump on. So we were sort of like a little bit struggling on.
Yeah. Okay. Then maybe with this context, we can go back to like looking at the results again, and then things will make more sense.
Yes. Okay. So I guess as I mentioned, they're sort of like sorted in the easy to the hardest, where puzzle is the easiest, and then scene is slightly harder, cube, triple, and cube quadruple. So the easier tasks, you can basically kind of like solve them by some degree in the offline case, because offline data contains enough information for you to actually know how to like do the task well. So you can see that our method actually performs similarly to the non-trunking method, which probably is because like we don't really have any thing that's added on top of what's already in the offline data. And our method really starts to shine in the online case. And as we've mentioned, our action chunking policy, because follows or stays close to the offline data by behavior constraint with this expressive policy, it can really generate temporally coherent actions to explore effectively online. So I guess cube double, you can already see a little bit that it improves the success rate quite a bit faster than our baseline. A triple as well, and it really started to kind of like take off on the really hard environment, which is cube quadruple, where you have to move all of the 4 cubes into the right location to solve the task successfully. And this is where having really temporally coherent actions is the most helpful.
So this is like, so cube quadruple, the problem is something like I have to stack these 4 different colored cubes in a particular order, right? So then the fact that your flow policy, you can sample these temporally coherent trajectory snippets, basically, which like let it try stacking all the different cubes in different orders. That's the magic, I guess. That means that it can grow, that it can do much better than the previous methods. Okay.
Yeah, that's the intuition.
Yeah, makes sense.
In practice, not all of you visualize the video, not all of the pick and place are perfect.
Sure.
They often fail and stuff like
that. But it is
also
like learning to pick and place better as it does this, right? Which is part of what makes it more exciting than the hierarchical version where it wouldn't be doing that, right? So
right.
Okay.
That's right.
Yeah. Okay. So something really interesting if you look at like these cube triple and cube quadruple graphs is that like you can see like the offline performance, whether you use queue chunking or not, like basically nothing really solves the task. But as long as you get a tiny bit of online interactions, basically just using R on top of that with coherent exploration, that gives you like so much performance gains. Basically, you're learning something meaningful offline with these temporally coherent actions that are not perfect. That doesn't solve the task, but once you start to adjust it a little bit, you can use this knowledge in a really efficient way. And I believe, Colin, if you go to the website, we will like the really cool visualizations that shows you like how the arm moves with or without queue chunking and how it explores online. Well, the right one is freezed, but it's
okay. Now I started.
Yeah, I feel like it's a very compelling visualization, particularly because I feel like if you've ever done RL for manipulation, it is really a pain to get them to explore very well at all. Like,
yeah,
I think
exactly. Yeah. Usually that's
right.
I have a question about it seems to me that success rate, especially for these like more difficult tasks, would you say they do plateau? I can't really tell because the triple one seems like if you do more steps, it might still go up, but then the other one, they plateau quite quickly. Like, what's your sense?
Yeah, so that's a good question. The reason why they plateau is, at least for quadruple, is because one of the tasks is really, really difficult. And this plot is an aggregation of 5 tasks. So let's go to the appendix.
Yeah, so basically what cube quadruple means is that there are different subtasks where the distribution of the cubes are different, and then some are more difficult than the other.
Yeah, that's right. So we have sort of the complete plot here where each row is one domain, and each domain has 5 different tasks. This is like all part of the OG benchmark. So you can see that task 5 for triple and quadruple, we actually couldn't solve them in our experiment.
So what's task 5?
Sorry?
What's task 5? Yeah.
I think it's like some very hard stacking task, I believe. Yeah. It's like, I think you're supposed to like stack all of them together. But I need to double check.
I see.
Do
Okay.
you know, Paul, what the task 5 is?
I don't know off of the top of my head.
Yeah, I just remember it was like a really hard stacking task. That's like really difficult to do.
So is it really difficult? Well, it looked like all of the methods were failing. So is it really difficult just in general, or is this a case where like perhaps the particular types of trajectory modes weren't well represented in the offline data set? Therefore, it's or both, I guess, because the offline data set couldn't handle it either. I don't know. So
that's a great question. So definitely if we increase the offline data size, this task becomes easier and easier. And this is because the particular stacking motion or the configuration will occur more often once you have a huge data set. I believe that if you train a goal condition RL, offline a goal condition RL agent with a really large data set, both triple and quadruple can be solved with 100% success rate. But it is really in this like sort of limited data regime where we can really solve them in the offline case. This is where we find our method, which is like doing action trunking with RL, doing effective online exploration is the most effective. Right. Okay. Let's go back to the top. Is there a couple more things I want to say here is that, yes, so we also tested on a big RoboMimic, a benchmark, which you might be more familiar with. Essentially, it's sort of a relatively more realistic benchmark where the tasks are kind of like lifting some object and putting like the square one is perhaps a little bit more like precise manipulation that requires you to like place a square object into onto like a square pole. The square has like kind of like a square hole in it, and then it requires you to kind of like fit onto a square hole. And this is one of the harder tasks that we found in our experiment, where we really found that having action trunking policy can both help offline and online in some sense. And this is probably because that these tasks are the ones that we know that imitation helps a lot, especially with action trunking. Action trunking helps imitation a lot. And we can see that we do have the offline improvement from this action trunking and the speed up from in the online case as well. Another thing that I want to like just briefly mention here is that there's an important ablation in our experiments, which is n-step return ablation. So what does this mean? We did say that there are two benefits of our Q chunking, right? The first benefit is like we have effective online exploration from temporally coherent action. The second benefit is that we do have this kind of value speed up from backing up the value n-step away, because we do have the Q function for an entire action chunk. So we can actually do value backup more effectively. So something here that we try to ablate here is that, okay, what if we do the same n-step backup? So backing up the value n-step ahead, and without really using the chunk policy or the chunk critic. So this is where we see that without using the chunk critic, you really suffer this like n-step return baseline really doesn't work really well in a lot of tasks. Although it does seem to have a good initial starting point, but eventually it sort of like underperforms than both of the Q chunking methods and oftentimes by the baseline method, which is without using the n-step return. So this is really to show that training with the chunked critic and chunk policy is really necessary for the performance gains that we're seeing right now.
Why would it be worse than the baseline, though? That doesn't quite make sense to me.
Yeah, so this is a very good question, and it sort of has to do with how sometimes the n-step return can be a little bit biased by its it's not like the most principled way of doing value backup. So we hypothesize that it's because of this like not so principled way of doing backup sort of leads to the performance degrade. I guess I could expand it a little bit more on this. Essentially, the intuition here is that if you use the replay buffer transition or the reward to back up your value, you're essentially backing up value that is part of it is from your behavior policy, part of it is from your current policy. So you're kind of like doing a mixture of both rather than doing it all on your current policy, which is what like a TD learning is supposed to do.
Yeah, but if you do the Q chunking backup where you back up the Q function in the action chunk space, you get to look n steps ahead because you have n steps of actions ahead, but you're backing up with exactly the unbiased action of your chunk policy. So that's why you enjoy the benefit of faster TD backup, but you don't suffer from this bias problem.
Interesting.
Yeah, so these are the two benefits that you can get with Q chunking. One is more efficient, more coherent exploration online, and the second is these faster TD backup, which is the two reasons why you see on a lot of domains that Q chunking learns much faster than the other methods, because it gets better data and it actually learns faster from that better data.
Yeah, it's interesting. It's a very interesting ablation that it matters so much that basically they need both. That it's not purely the exploration, I guess. Great. Well, are you gonna try it on a real robot at some point, sir?
Yep, I think that would be cool.
I think that'd be cool.
Yeah, so I think one difference here, or like one particular difficulty when trying on the real robot, is that as you said, Chris, like the Q junction space on a real robot could be like really large. Right? So with a typical action chunk of 50 over like 6-7 DOF arms, you essentially blow up the action dimension a lot. And I think an interesting piece of research there is that how do you deal with this high dimensional action space, or how can you map this high dimensional action space to a lower dimensional action space and learn on the lower dimensional compressed action space?
Well, isn't that essentially what you're doing though by sampling from this flow model, is trying to learn on a lower dimensional action space? But I guess
so
you just need further reduction, you think? Yeah,
so that really so that really constrains your policy quite a lot, right? So that means you're traversing this very fine manifold in the high dimensional action space, but it could still be hard to learn your Q function if your Q function is a very high dimensional thing.
Yeah, hopefully the Q function wouldn't be that hard, because like if you think about it, the learning problem is not that difficult if you constrain your space of input that you can take. So in some way, we're operating in effectively a very low dimensional learning problem for the Q function as well. So I think this part of why it works so well in our setting is also because that the Q learning doesn't really need to learn all kind of like different actions. It's possible it only needs to learn like a very small manifold of action chunking distribution that really really reduce the complexity of the Q value learning.
Yeah. So I think this is like a very exciting thing to try, and it's like actually a very, very easy thing to try, because essentially you're not really changing much of your algorithm. You're essentially you need to do everything in action chunk space. You need to have a behavior regularization. If you're doing robotics, you're probably already using an expressive diffusion policy. So it really just requires changing a few lines of code. And so that's why we're very excited to tell the community about like this finding that we have, so that basically everyone can change a few lines of code and basically just do everything in action chunking space, which I think makes more sense if you're doing any kind of offline to online experiments for reinforcement learning or reinforcement learning fine-tuning on robots.
Yeah, especially since like this is like you're saying, like almost everything that you see these days. Like there was the figure helix video today, right?
Yeah.
Which is like that's all using action chunks, right? There's every one of these major VLAs is doing something like this. Every company's working with these. Like it makes a lot of sense.
Exactly.
It's nice that there is an answer that you can just directly use these for reinforcement learning. So it's nice.
Yeah, exactly. Yeah. It's kind of like a little decorator on top that you use to really perfect your success rate of your policy.
But I imagine when you actually want to do the online part with real robots, there are real constraints.
There are definitely real constraints.
Like you have to kill a robot in the process, and then you can't do the next attempt.
There are a lot of like robotic specific problems, I guess, of like, how do you determine success? How do you do the resets for the environment? Is there train test distribution shift? What skill are you actually improving? So but actually a lot of those would like somewhat get better if you're leveraging your offline data set better. So this method can potentially be somewhat of a fix to those problems.
So I guess like one caveat also along that side of like real robot learning is that if you notice the number of steps here is in 10 to the power of 6, which is in millions. Yeah. So each dot here means 100K steps in terms of the environment. So that's a lot of steps, obviously. But this is also because we test with an extremely low update to data regime, where we are only updating one we're only updating once per environment steps. So there are a lot of like interesting or exciting future work to how do we actually make it super, super sample efficient, building on top of this, like sort of the observation that we can just apply action chunking to the algorithm and then make it can already explore much more efficiently. Can we make it actually more really, really sample efficient? Can we actually just do it within 10 episodes of online data collection? They can actually learn really, really well.
Yeah.
So I feel like there are a lot of really exciting problem building on top of this, either applying to real world robots or even just more like iteration in the sim, how to like actually make online RL algorithm really, really efficient for action chunking policy. And even beyond action chunking policy, I believe that there's a whole class of non-Markovian policies if we can manage to train them in a very practical way and learn very simple, efficiently online to do effective exploration. I feel like that would be pretty impactful for RL in general.
Yeah, I mean, on that note, I also do imagine that like the real robot case, the most relevant one, right? Like was probably going to be not starting at 40% accuracy or 50% like you do here, but starting at like with enough data to get to like 80 or 90%, where you probably have like much more offline data to learn from, and the robot's already probably performing pretty well, but not perfectly. And like that's the case where hopefully the exploration is really effective, right?
Yeah.
Like
hopefully.
yeah, hopefully.
I guess we'll see.
Yeah, exactly. Like, yeah, I think then you just really need to go like climb that last 10, 20% of performance. And I think what Colin just mentioned, something that's really interesting is that one of the knobs you can turn to make our algorithms more sample efficient is this thing called updated data ratio, or UTD, which is basically the idea of you can collect a batch of data. Instead of doing one update on it, you can do several updates on this same batch of data. And so what that means is basically for the same amount of data, you can update your values and your policy much faster. So one very exciting thing to study is that, we have an ablation here, is that you can try to use a higher update to data ratio to make your algorithm much more sample efficient, so that when you're doing this on real robots, you don't have to collect millions of episodes. You just collect a few and then you keep updating on it.
And this is mostly powered by the fact that individual samples here are much more informative because they're drawn.
Yeah.
They're actually, okay.
Yeah. So this is actually kind of like one of the future work that we hope people can address, because in our experiments we didn't really find cranking up the update to the ratio just naively works. There are probably other things that we need to take care of to actually make it work so much better, right? So that's like kind of like an exciting opportunities.
Yeah. So one of the things in tuning these things, tuning the updated data ratio, is that it has a very interesting interplay between your model size, your updated data ratio, and your batch size. So one of the works at Berkeley that's about to come out in the coming weeks is exactly studying how you can how do you actually tune these hyperparameters? How do you effectively select UTDs, batch sizes, and model size to really scale up and make reinforcement learning much more sample efficient? So there are a lot of interesting questions here that can try to really push the performance of these methods.
But I'll say maybe instead of like bigger future work, like if you guys just have maybe a couple more months on this research, like what would be something that you just want to push a bit more? Like would you have done even more steps of this, or what would you have tested? I think you mentioned there's in the revision you're adding a few more things, right? So what would be the one or two things that you wish you have time for and would make this an even better paper?
Yeah, so definitely comparison with the skill-based method will be a good addition to the current paper. And also, if I have more cycles to experiment with things, I will also want to test out more realistic environments. Robots is always hard to do experiments with, but maybe some simulation that's like closer to the real world scenarios, something more along the line of like the RoboMimic domains will be nice. We currently only have 3 tasks, which I feel a little bit shaky on that front, but I think like the scientific finding here still holds. It's just like I hope we can have more on that. And perhaps a little bit more on the algorithmic side is like, how do we actually figure out a way to do action chunking, but without fully being open loop will be super impactful. And that is something that I will probably focus on the most algorithmically in the couple months, other than just pushing in the exact same idea for more experiments, because essentially it gives more flexibility on how optimal the policy could represent and how much it can essentially expand the capability of the policy or the size of the policy class. And figuring out how to make that more feasible will be a pretty interesting thing, or maybe a pretty useful thing for just RL and exploration, online exploration from offline data in general, which is like what I'm pretty excited about in general.
Yeah, so yeah, Colin has covered a lot of the great algorithmic points that are like great immediate future works. I think one more point I'll add to that is I think it's actually really exciting to try to really push for this and make things work on a robot. Like a year or a few years ago, like if you try to learn like an insertion skill from like a Franca arm, it would take like more than an hour to do online RL exploration and then like just simple insertion skills. And then Colin and I had a previous paper called Warm Start RL that basically is an RL fine-tuning method that really tries to push it down to about 15-20 minutes. And I think one really exciting idea is that like if we can include action chunking successfully, it would be really useful if we can get it to work in a few minutes, like under 5 minutes of RL fine-tuning. Then you can use this essentially as a method to perfect your policy success rate to near 100%, or you can use this as a really expert data collection method for new tasks that collects really good data for you.
How much do you think you could push like pre-training for this? Like if you used like Pi0 or something to seed the model, like some real like VLA foundation model, do you think it would work?
Yeah, I think we have made a lot of progress as a community on the policy side. I think the bigger question is how good of a critic we can learn on the like a large data set over the action chunk space.
Yeah, I guess maybe a typical final question we always ask, like any cool papers you guys came across recently that you want to give a shout out to? Maybe we can invite them for the next podcast too.
Andrew, DSR.
I think my take on it is, I mean, as a layman, observing these things from like nearby, but still I'm not a researcher, right? So I think it just makes sense to me. Like my intuition is that like you want this concept action chunking to be just it's a more temporally consistent thing to train on in general, right? Yeah. Whether it is you're doing like in diffusion policy or you do an RL, like I think your point also that and clearly your results do show if you start off with some based on like expert data, and once you do it a bit online, then maybe that makes it actually feasible to do it in the real world. Because like the absolute success rate, I think, is quite critical. Otherwise, you're just gonna break your robot instantly. But if you're starting with something that actually that becomes like, I mean, what you mentioned, Paul, just now, like 5 minutes to learn something very, very specific, I think it has a lot of real implications. Like 1 hour, I think is not practical. But once you get in minutes, I think if you tell my mom, say, hey, I'm gonna give you a robot like that's gonna learn within 5 minutes, figure out how to do like how to use a specific knife, I think should be okay. But if it's anything more than an hour, I might as well just do it myself. So I think these things do actually matter ultimately to and so we're getting maybe in the next few years like getting into a range where these things actually are the one that makes jump from research to real production use. Really excited about this.
Yeah, exactly. If we can get it down in minutes, I think it will have huge user input.
Okay, cool. Sounds good. Right. Thank you so much for your time again.
Thank you guys for coming. Really exciting stuff.
Rewatch this whole
episode.
Thank
you for inviting us.
Thank you for the invite again.
Thanks for all the sharing, man. Okay, cool.
Cool.
See you guys soon.
All right.
Okay, Chris, what have you learned?
So I think, this was a really interesting paper. I feel like I really liked the ideas here of like learning to use action chunks for exploration, because it is the way that everybody does everything these days, is predicting these little trajectory snippets, and it doesn't really mesh that well with reinforcement learning as they were talking about. It's a nice way of, I can go on to this. There's because we talked a little bit about hierarchical RL and things like this. So like stuff that I've worked on for a long time is like hierarchical learning and like action primitives and so on. For like, this is one of the ways that we get learning for demonstration and exploration work really efficiently, has always been these action primitives. And this is like a nice, compelling way of making reinforcement learning, of making this like actually kind of data driven as opposed to like designing all this stuff. There's a nice parallel there to like how like deep learning got rid of all this structure we used to use for vision. So anyway, I really liked it. That is really interesting work. I really think there's a lot of potential there for future stuff. Although, of course, they didn't actually test on real robots. There are still these dimensionality issues, so we'll see. But yeah, I think it's really exciting. So yeah, what did you think?
Yeah, I think I mean just from a layman perspective, like I mentioned towards the end, like to me it just makes sense. Like things should be done it's a series of motion. Things needs to be temporally consistent. So insofar action chunk is that it help you to express that temporal consistency. I think it makes sense. And yeah, I think whatever like the final outcome should be. I think that the question of doing RL in the real world is always is you cannot do it in the real world. Your robot will break in the the moment you switch it on. But if you have if you like the kind of what they have, right, all the charts are basically two parts, right, offline and then online. If you can get the offline part already, I mean absolute maybe at least 90%, and then you quickly get the online spike, and then that gets you very close to 100%, and that makes it very applicable to in real robots. And so I think for some of the simpler tasks, they probably can do it already using this.
Yeah, so I'm really curious as to what would happen if you just like tried using one of these big VLAs or something like that to set up the diffusion space. Like I think that there's like it feels like you should be able to learn to explore really efficiently if you did this like really at scale. And that would be really like you're saying, because then you could actually like do this quickly. Also, I feel like at some point you're gonna have to start calling yourself a layman now that we've been doing this for 6 months. And,
Okay.
make all this.
I mean, non-researcher, but like observing closely. I think these things, but obviously I have to do the research myself. The other thing I thought would be interesting to they mentioned something about like having the action chunk length also be a dynamic thing that hyperparameter that can be learned. Because I'm just thinking again, like how do I do things like even though we do things mostly subconsciously, right? Like, but I think there is probably a variation. I don't know whether context window is the way to think about it, like attention span. It's like maybe when I'm driving in a car park, right? I need to be fully attention, and so I'm ready to react. And then when I'm just driving on the highway, my mind switch off, like, but then when something happens, as a human, I'm able to slip into the pack. Like, okay, now I need to be. My action chunk is probably damn small, So there is something that is I don't know, like whether that's the right way to think about it, but like, action chunking not being like a fixed thing, that's something that it's react to online. I think it's good to investigate.
Yeah, I agree. There's like a lot of potential there. Yeah, I'm not sure how you're gonna do that. Tricky stuff.
Okay, cool.
But cool.
Yeah, okay. Until the next one. We'll chat soon.
Cool. Sounds good.